Good morning, everybody. It's time to do some math. Okay, so I'm going to go through a few things that are already on the sheets that I've sent you. Now, for some of you, it might be useful just simply to follow along with me talking about it. I figure for many of you, this is going to make it a lot easier to understand. Sometimes when we just read notes, they don't really help us out all the time. It's better to have someone kind of like follow it through with you. So we're going to cover a little something, a word problem, and it's the one I left you with at the end of the last class. And we're going to go through that, and that'll give us one more little bit of multiplying radicals, but then we're going to jump right into dividing radicals, which is not something I've covered with you yet, and I want you to be able to do it on your own. So you'll just be using the sheets you got. I expect you all to be doing some work on all of those 4 worksheets you have. So there's quite a bit of stuff. Is it 4? I think it's 4. Should be covering adding, subtracting, dividing, and multiplying. So get the practice in because we will be jumping onto something new on Monday. So this is more or less homework. So let's just get right into this question here. Determine the area and perimeter of the inner square. So the only information I have so far is that there is a side to the larger square that is 8 centimeters in height, and it's a square, which immediately tells me that this is 8 as well over here. So the question is if I want to get the perimeter and the area of the inside square, I really need to know one of these lengths. So how do I do that? Well, if I look at this sort of this right here, this triangle here, well, first off, I know I got a triangle. So let's just take a look at that on its own. So I'm going to have a piece there. That's the side I'm looking for. So I'm looking for x. I know that this is 90 degrees because it's part of a square. And I also know that this inner square, in order to be a square, it must have all sides equal, which means this distance has to be at this point here, has to be at the halfway point. So I know that this is a length of 4, and I know that this is a length of 4. So already I'm set up to do this right. I can find out what x is just by simply using the Pythagorean theorem. So Pythagorean theorem, if we, at this point I assume you totally know what this is, but c squared equals a squared plus b squared, and then I'm just simply replacing everything. So the hypotenuse, the c part, is my x. So I'm going to have x squared is equal to 4 squared plus 4 squared. And with that, x squared is equal to, well, what do we got? 16 plus 16, so that'll be 32. And then I got a square root. Now normally I know you do plus or minus. You're supposed to do plus or minus here the root of 32, but there's no reason to include the minus because I'm dealing with something that is an actual length, and there's no such thing as a negative length. So I won't even bother with saying plus or minus. I know the answer must be the positive. So right here I've got a radical, and I want to know how much I can simplify that down. I don't want to be just simply setting that up. So let me see, 16 times 2, yeah, and 16 here, I can do a nice even square root. It's one of those nice ones like 36 or 25. So I can take that out as a 4, so I'll have 4 root 2. There's my answer. Okay, so 4 root 2 is 1 length. So now if I'm looking for the area, that's nothing more than length times width, and I know both length times width. So what I'm dealing with is 4 root 2, and it's squared, or rather it is the length times the width. That's another way of looking at it. So what does that look like? Okay, well, I'm going to have the coefficients, the outside numbers, multiplied together. That's the rule of multiplication. 16, and then root of 2 times 2. This is looking good. 16 root 4, and I know what root 4 is. That's 2. So I'm going to have 16 times 2, 32. And if you think about that, kind of makes sense, since x in this case is root 32. X squared must equal root 32 to the power of 2. And remember that what I'd said about square roots, that actually is 32. If I had to write it out as a power, it's 32 to the half. And 32 to the half squared, what do I do in this case? When I have a power inside, outside, one in brackets, I multiply those together. So I'm left with a 32 to the power of 1/2 times 2, or rather 2 over 1 if I want to say that. And if you look at that, what happens is the 2's cancel, and I'm left with 32 to the 1, which is nothing more than 32, which is the same number over here. Perfect. Okay, so there's a few ways I can look at it. How about perimeter? Perimeter. Well, that's just all four sides added up, and so I'm looking at 4 times one side, which in this case is 4 root 2. There is no radical on the 4. It's just a 4. It's just a coefficient, so I'm just multiplying the outside numbers. So it's 4 times 4. I'm going to be left with 16 root 2. So there you go. I got my answers. I got 16 root 2 for my perimeter, and I got 32 for my area. And there we go. That's it for multiplication. So this is where usually that the multiplication leads to some sort of word problem, and we have this kind of thinking. Geometry gets involved quite a bit, because obviously once I start using the Pythagorean theorem, I'm getting some square roots. I could do something that involves some triangles in different ways. That would also maybe sines and tangents. Perhaps a tangent is a length over width, the opposite over adjacent, and perhaps one of these things gives me a square root. It's the kind of questions you got to expect to find here. Okay, so let's move on. Now we're going to talk about dividing radicals. So it's the last thing we're talking about. What are the rules for dividing things up? And here it's stating it. When I'm dividing, I divide coefficients by coefficients, and I divide radicands by radicands. Okay, what does that mean? Well, let's just look at it. In general, let's say I've got some number and some root of a letter A, and I'm dividing by a different number. Now notice, it's the same index number, K and K. Same index number. You cannot divide, well, you can, but not in this way. We'll get into that later. If we look at the powers, there's ways we can do this. But right now, what we want to know is, can we do this easily? No, you can't. You want to make sure that the values of your index numbers are the same, or this doesn't quite work out. So when I say you divide coefficients by coefficients, I'm talking about these numbers. So you divide m by n, and then I divide the radicands together. So I can put both of those in the same square root. In other words, this really can be looked at as a divided by b, both inside the root. Sorry, I forgot the k there. So that's generally what I mean by what I'm saying up here. So how does that work? Let's take a simple example. And since I only got what looks like 6 minutes, so I'm going to be really quick here. Let's take a good example. This is on the sheet, so you can just take a look at it. I got 2 root 54, and I'm going to divide that by 5 root 24. Now the first things I want to do is I want to simplify. I want to basically get some simplification and see if there's anything that will cancel out. That's what I want to do first. So 2 and 5 is 2 and 5. There's nothing I can do about that. So I'm going to have 2 divided by 5. Let's do equals there, sorry. Now, what can I do with 54? Well, 54, now the way it does it on the sheet is it looks at specific parts. But I'm going to just totally break this apart. 54 divided by 2, what is that? That's 20, holy cow, what is that? 27. Okay, so 27, so 2 times 27. 27 divided by 3 is 9, so 9 is 3 times 3. So 2 times 3 times 3 times 3, that's 54. and I divide by the root of 24. So what's 24? Let's say 4 times 6. So 4 is 2 times 2, and 6, 2 times 3. So when I'm looking at that, I'm looking to see what I can cancel out. Okay, so let's just take a look. Well, I got a 3 here and a 3 here. Okay, that's gone. I got a 2 and a 2, and now I'm stuck. There's nothing left. Okay, so that's as far as I go. So then I get to look at what I got left. I got 2 over 5. So 2 over 5 times the square root of 3. Whoops, no, it's not 3. It's 3 times 3. Square root of 9 over 4. Now I can look at that in a different way. Let's just look at that. Now, just in the same way that I could take both separate roots and make them a single root, just like I'm doing there, I can break them back down into separate ones again. So that's actually equal to 2 times on the top root of 9 divided by 5 times root of 4. And in this case, 9 and 4 are perfect squares, so I can easily say that this is the same as saying 2 times 3, square root of 9 is 3, and 5 times the square root of 4, 2. And I end up with 2 times 3 at the top, 6 over 2 times 5, 10. Fantastic. So I get this really nice, and in fact I can even reduce that even more. 6 goes in, I can drop that down by 2. 6 divided by 2 is 3, 10 divided by 2 is 5. So I'm left with an answer of 3 over 5 for my final answer. Okay, now the only other situation I want to look at, that's a typical case. So you can see how we can break the thing apart, cancel some stuff out, simplify the whole thing down. It doesn't always work out this beautifully. Sometimes you're going to have a root somewhere, and what we do want to do is occasionally rationalize what we call rationalizing the denominator. In other words, when we deal with radicals, we really don't want to see a square root on the denominator. If we can, we avoid it. And you might remember we had said at one point that 1 over root 2 is the same as saying root 2 over 2. And the reason why we were doing that, remember when we were doing angles, we had that a lot. The reason we're doing that is because we just didn't like having a 1 over a square root. And the only way to do that was to, in this case, how did we get that? Well, we took a 1 over square root 2 and we multiplied by 1. But it wasn't just any old 1. It was a square root 2 over square root 2. And that is just 1. That's any number divided by itself is 1. But we've done it in order to basically get rid of the square root at the bottom. Because what happens there? We get a square root, 1 times square root 2 at the top. Fine. But a square root 2 times a square root 2 is the same as saying square root of 2 times 2. 4. Square root 2 over 2. So very useful. Very useful. Something we want to get used to doing all the time. So what we want to do is, once we have a situation where we have an answer, is find a way of rationalizing that denominator. So let me see, how else could I put that? Let's try another example. I'll do one right at the bottom here. 7 root 32y over 5 root 63. Okay, so what's that look like? Well, first off, I want to see if I can't cancel anything out. So what do I got? I'm going to have a 7 root. Now what does this look like? This is, I could say 32y is the same as saying root 16. There's a 16 into 32 times root 2, but now I got to get the y over, so I'll put the y over here. That way I single out the 16, because 16 I know I can do something with. At the bottom I got 5 root 63. 63, that's 9 times 7. Okay, so these guys I know that's going to turn into a 4, and this is going to turn into a 3. So what do I got? What do I got? I have 7 times 4 root 2y, different color there, sorry, 5 times 3 square root of 7, and then I'm going to leave you to do the rest.